Now, I know last week we were discussing electrons and like end shells and all that. Are we
Mhm.
gonna deal with electron configuration at all?
Yeah, that's this chapter.
Okay.
Yeah. Okay. All right. So we're in business here. All right. So chapter 8. So first thing we're going to talk about is how the orbitals are arranged in the atom in terms of their energies. And hold on 1 minute. Okay. So I want us to start off with looking at what we have here on the screen. Now, on the left, we have basically how the orbitals are arranged in terms of energy for the hydrogen atom. Remember, the hydrogen atom has only one electron, all right? And basically, in this case, you'll see that the first shell will have the 1s orbital, and then the second shell will have the 2s orbital plus three 2p orbitals, and then the third shell will have 3s, 3p, and the 3ds, and so on and so forth, right? So that's basically a simple arrangement of how the orbitals, in terms of their energies, are arranged in the hydrogen atom, all right? So there's a term which I don't remember if it's in your textbook, but whenever you have a set of orbitals that are equal in energy, we say that they're degenerate. So let me just write down the definition here. So degenerate orbitals are orbitals of equal energy. All right. So if you look at the diagram I was just referring to, for example, in the second shell, you have the 2s and 2p subshells within the same shell, and as you can see, they have the same energy. So we say that the 2s and the 3 2p orbitals are degenerate because they have the same energy. And you can apply the same term to this set here where the 3s, the 3p, and the 3d orbitals are also of the same energy. So that's what the term degenerate means. Now, this is what happens in the case of the hydrogen atom. Now, the diagram on the right is showing you the arrangement for a typical multi-electron atom. So basically, we're talking about atoms where you have two or more electrons present, right? And there are two important differences that you'll notice when you compare the situation with a hydrogen atom and that dealing with the multi-electron atom, right? Now, hold on 1 minute, so what's going on here? Okay, why is this thing not responding? Okay, one of the differences is that in the case of the hydrogen atom, the orbitals or the subshells within the same shell have the same energy. That is not true in the case of the multi-electron atom. So for example, in this case here, you'll notice that the 2s sublevel is lower in energy compared to the 2p sublevel, even though they're in the same shell, right? So basically, that's what you observe here when you compare that to the second shell here. And then when you compare the third shell in the case of the hydrogen atom to the third shell here, again, you see the same thing. The sublevels within the third shell are not all equal, all right? So that's one important difference between the hydrogen atom and a typical multi-electron atom. Another difference has to do with the fact that the shells in the case of the multi-electron atom will be of a lower energy. So for example, the 1s orbital here from the first shell has the energy here, but in the case of the multi-electron atom, that 1s orbital or 1s subshell is of a lower energy. The same is true for the second shell. The second shell is right here in terms of the energy. Here it's lower, and so on and so forth for the third and fourth and fifth shell and beyond, all right? So those are the two important differences between the hydrogen atom and a typical multi-electron atom, all right? So with that said, let's see what's next. Let me clear this here. Okay, so now we're going to talk about the electron configuration. Whenever you hear that term, what it's referring to is how the electrons are distributed among the subshells within an atom, and also among the orbitals, all right? So there are two different ways, two main ways of representing the electron configuration. One is called the SPDF notation, right? And it looks something like this, right? So typically, when it comes to the SPDF notation, it shows you where the electrons are located within a particular subshell, right? And of course, which shell that the subshell belongs to. So for example, if you look at what is here, what's going on? Right? You see 1s2, right? This one represents the shell that we're referring to. S here represents the subshell within that shell. And this 2 here, written as a superscript, is the number of electrons present within that subshell, all right? So if you see something like, let me go back to this here. If you see something like this, 1s2, 2s2, 2p6, right? That basically represents how the electrons are distributed in the case of the element neon, right? So what this is saying is that within the first shell, you have 2 electrons in the S subshell. In the second subshell, you have 2 electrons in the 2s subshell and 6 electrons in the 2p subshell, all right? So that's basically how you interpret the SPDF notation when it comes to writing down the electron configuration. Now, another way of writing down the electron configuration is using what is called an orbital or box diagram. And in this representation, the boxes represents the orbitals, right? And we use arrows to represent the electrons. And this actually gives more information about the different electrons and where they're located within the atom. So in the case of nitrogen, example given here, right? This box here represents the 1s sublevel. This box here represents the 2s sublevel. And these 3 boxes represents the 3 p orbitals present in the 2p sublevel, all right? And also, it shows you how the electrons are spinning, right? Remember, I think I mentioned earlier that if you have an orbital, then 2 electrons occupying that orbital must be spinning in opposite directions. If I haven't said that before, we're going to encounter that later on, right? So that's what's being shown here. You have 2 electrons occupying the 1s orbital. They're spinning in opposite directions. Here we have 2 electrons in the 2s sublevel spinning in opposite directions. And here we have 3 electrons, each of them occupying a p orbital, a 2p orbital. And they're all spinning in the same direction, right? Now, if I were to write down the SPDF notation for this, it would be 1s2, 2s2, 2p3, all right? So that would be how you would represent the electronic configuration using the SPDF notation. Okay, now let's talk about the rules. And these rules are specifically for the ground state configuration of atoms, right? Remember, the ground state configuration, what we're referring to is the most stable configuration, the lowest energy, all right, that the system will have, right? So there are some rules for you to determine the ground state configurations of different atoms. So the first one is that electrons ordinarily occupy orbitals of the lowest energy available, right? So basically what this is saying is that the electrons will simply go into the lowest energy orbital that is available to it. The second rule has to do with what is called Pauli's exclusion principle. And this basically says that in any atomic orbital, it can accommodate no more than 2 electrons. And if those 2 electrons are present in that orbital, then those electrons must be spinning in opposite directions, all right? So that's what Pauli's exclusion principle is saying. Another way of stating this particular rule is that no 2 electrons in the same atom may have all 4 quantum numbers alike, all right? Now, the next thing we have to be aware of is that if you have a set of degenerate orbitals, right? In other words, orbitals of the same energy, then what will happen is that the electrons will enter the empty orbitals whenever possible, right? So let's say you have 3 p orbitals, right? In the ground state, you will not have 2 electrons going into 1 p orbital, right? For example, basically 1 electron will occupy one of the p orbitals, and then another electron will occupy another vacant p orbital, as an example. So this is called Hund's rule, right? And in addition to that fact, according to Hund's rule, whenever you have electrons in half-filled orbitals, they must be spinning in the same direction. That would be another requirement for the ground state configuration. All right. Okay. Another rule. Oh, sorry. I think that's it as far as the rules are concerned. Now, one issue that oftentimes people face when learning this for the first time is how do we know the order of the orbitals? Because we need to know that in order for us to get the correct electron configuration. Let me go back to our previous slide to explain something, because what you'll find is that as you go up in energy for the different shells, what you'll find is that at about the third shell, between the third and fourth shell, what you'll find is that the highest energy subshell would be higher in energy compared to the lowest energy subshell in the fourth shell. So the highest energy subshell in the third shell would be of a lower energy, or a higher energy, I should say, compared to the lowest subshell in the fourth shell, right? So there's some overlap. And that overlap kind of increases as you move up in terms of the energy of the shells. So it's very difficult at face value to make a prediction as to what the exact order of the orbitals is. So somebody, I don't know who, came up with this diagram, right? Basically, this is what you use to help you to establish the order of the orbitals in terms of energy, right? So basically what you do, I remember when I was a student to remember this, what I would do is I would write on a sheet of paper 1s, 2s, 3s, all the way down to 7s here. And then I would start at the second shell to get the P sublevels, 2P, 3P, 4P, 5P, all the way to 7P. And then I'll start at the third shell here to get the D sublevels. And then at the fourth shell, the F sublevels and so on, right? And then I'll draw an arrow as shown here in each case. And then I would establish the orders by following the arrows from tail to head, right? So the first orbital in terms of energy, the lowest energy orbital would be the 1s orbital. Then you have the 2s, then you have the 2p, 3s, and then you have the 3p, 4s, and so on and so forth, right? So that's important, right? You need to establish the orders of the orbitals, because when you're trying to determine the electron configuration of a particular element, what you need to do is start from the lowest orbital first, and then if you have more electrons, you continue to add them accordingly, right? So in order for you to get the correct distribution, you need to have the correct order of the sublevels in terms of their energies, right? Let me also say that even though we have this pattern here, there are some exceptions to the filling order for the heavier elements, and we won't spend too much time looking at those, all right? Okay, so now we're going to get to how do we determine, or how do we assign the electrons to the subshells. And the principle that is employed here in this particular exercise is called the Aufbau principle, right? Aufbau, I think, is a German word for building up, all right? So we're going to see how this works, starting from the smallest element in terms of the atom. And we know hydrogen has only one electron. So that electron will go right into the lowest orbital, lowest energy orbital, which would be the 1s orbital, all right? So therefore, the electron configuration of hydrogen is 1s1. The next element is helium, for which the atomic number is 2, right? So therefore, those two electrons will go into the 1s sublevel as well. And there's only one s orbital present in that sublevel, right? And each orbital can have a maximum of 2 electrons, right? So basically, as far as helium is concerned, that sublevel and that shell is completely full, all right? So if you were to get to the next element, which is lithium, which would require 3 electrons, the first 2 electrons will go into the 1s sublevel. That is full, which means that the other electron now will go into the next higher sublevel, which would be the 2s sublevel. And therefore, as a result, the electron configuration of lithium is 1s2, 2s1. Okay, now, let us look at how do we determine what is called the noble gas core abbreviation configuration, all right? Because as you can imagine, if you were to continue this process and you get to something heavier, like iron, for example, you'd imagine that there will be a long string of characters, right? 1s2, 2s1, 2s2, and so on and so forth, right? So in some cases, you don't need all that information. In some cases, you only need the outer shell electron configuration or whatever, right? So that's the reason why another way of expressing the electronic configuration is using what is called the noble gas core abbreviation, all right? So in other words, the more abbreviated version, all right? So how do we get the abbreviated version? Well, basically what you do is start off with the electron configuration of the element that you're concerned with. So let's say you want to do this exercise for lithium. So this is the electronic configuration of lithium, right? And then what you do is consult the periodic table, right? And you look for the group 8 element that immediately precedes that element. So in the case of lithium, the group 8 element that comes immediately before lithium would be helium. And the electron configuration of helium, as we said before, is 1s2. So to get the abbreviated version, what we do is we replace this part here, which is equivalent to the configuration of helium, with the symbol of helium within square parentheses, right? So therefore, we have helium within square parentheses, and then we write down the rest of the configuration, which would be 2s1, and this would be the abbreviated version, right? Now, you might be wondering, okay, well, why do we say this is abbreviated compared to this? Because this and this is about the same in terms of length, right? And that is true in this case. But if you look at heavier elements, then you're going to see the difference between the standard configuration and the abbreviated version. In fact, the next example is that of titanium, right? So titanium has an atomic number of 22, right? If you were to write out the entire configuration of titanium, it would be 1s2, 2s2, 2p6, that's 10, then 3s2, then 3p6, then 4s2, so that's 10, 10, and then 3d2, all right? So this would be the entire electronic configuration of titanium. Now, as I said before, to get from this to the abbreviated version, what you do is consult the periodic table and see which group 8 element comes before titanium. So when you do that, in this particular case, you're going to see that the group 8 element is argon. And the argon configuration is equivalent to this right here. All right? So this part here is the argon configuration. So what you do in order to get the abbreviated version is replace all of this with the symbol for argon in square parentheses, as you can see here, and then you write down what is left, which would be the 4s2 and the 3d2, and that is it, all right? So that's basically, and here you can see the obvious difference between the standard configuration and the abbreviated configuration, which is much shorter, all right? So that's how you get from the standard configuration, which is longer compared to the abbreviated configuration, all right? Okay, so with that said, let me start you off. I hope I have enough of these here. Assignment number 8. And we're going to concentrate on the first part for now. Want to pass down. Take one and pass down to her. And for you guys out there in Zoom, I'm going to publish assignment 8 right now. So let me go here, 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 and publish chapter 8. Okay, so you guys out there in Zoom should now be able to access assignment number 8. I'm going to put it up now. Okay, so this question, we're going to concentrate for now on the first five, all right? So in part A, so this question says, in the space below, write the unabbreviated electron configurations of the following elements, and it gives you the different elements. Now I'm going to need your help because I don't memorize that same diagram I showed you. So if you can pull it up on your devices or if you have it in front of you, keep it at hand because I'm going to need it for especially the heavier elements, all right? Now let's start off with sodium. So the first thing I would do in order to answer this question is look up sodium in the periodic table. If you do that, you're going to see that sodium has an atomic number of 11, right? So we have 11 electrons that we have to distribute among the orbitals. So the first orbital would be the 1s orbital, and it can have a maximum of 2 electrons. And then the 2s orbital, which will itself have a maximum of 2 electrons. And then we have the 2p orbitals. The maximum number of electrons within the p sublevel will be 6. And then finally, the next orbital would be the 3s orbital, and the maximum number of electrons there would be 1, and that's it. All right, so that's basically how you determine the electron configuration of sodium. One thing I should mention, and I probably should have mentioned it before, one key thing you need to remember when it comes to the sublevels is what the number of orbitals are within, the maximum number of orbitals within the sublevels, and as a result, the maximum number of electrons, right? So remember now, each sublevel, or each, I should say, orbital can have a maximum of 2 electrons, right? That's a maximum, can't get beyond that, right? For the s sublevel, there's only one s orbital, right? It doesn't matter if it's 1s, 2s, or 3s, right? Only one s orbital can be present. When it comes to the p sublevel, there are 3 of them, right? Again, 2p, 3p, and so on, right? There are 3p orbitals. When it comes to the d orbitals, there are 5 of them. And when it comes to the f orbitals, there are 7 of them, all right? So you need to remember those numbers, right? And therefore, as a result, the maximum number of electrons that can occupy the s sublevel will be 2. The maximum number of electrons that can occupy the p level sublevel is 6. The maximum number that can occupy the D level would be 14, and then the maximum number that can occupy the F level sublevel is no, D.
SPDF.
D will be 10, F will be 14. All right, those are the maximum numbers, right? When it comes to those sublevels. All right, so that also comes into play in terms of distributing the electrons. So let's look at iron. Can somebody confirm this? Iron has an atomic number of 26.
Yeah.
Okay, good. Right. So 26, right? So 1s2, 2 electrons will go into the 1s sublevel, then 2s2, then 2p6, then 3s2, right? And then 3p6, and then 4s2. So that gives us 20. So 3d 6 would be it. That's the electronic configuration of iron. All right. Okay. Any questions so far? Any questions? Any questions? Okay. Again, somebody tell me, what's the atomic number of bromine?
It's B.
I'm sorry?
35.
35. Okay. Now, in this case, I'm going to need your help because I don't remember anything beyond 3D. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d 10, right? Whoops, sorry. I forgot to put a D. So this will be 3d 10. All right. So what comes after 3d? Can anybody?
It's going to be 4P.
I'm sorry, 4p? Okay. And so far we have 30 electrons distributed, which means that the p sublevel here would have 5 electrons, and that would be it. All right, so that would be the electronic configuration of bromine. Okay, any questions about this one? Any questions? Okay, again, I'm going to need your help. What's the atomic number of barium?
56.
56. All right. And
BA, right?
yeah, BA, yeah.
Yeah.
And again, I'm going to need your help beyond 3d10. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p6. Okay, and then
And then we need
that will be 36 so far. So what comes after 4p?
5s.
5s2. What comes after 5s?
It's gonna be 4d.
4d10. Let's see. So far we have
'Cause it's in,
36, 38,
it's in the 6th row.
48. So what's the next sublevel after 4d?
5p.
5p.
We need 5p6.
5p6. And then so that's what now? 36, 38, 48, 48 and 6, that's 54. So we need
6s.
6s2. Okay, and that's it. And that would be the electronic configuration of barium. Okay, any questions about this one? Any questions? Any questions? Okay, zirconium. What's the atomic number?
What's the abbreviation for it?
40.
40. Oh, the abbreviation
It's 0.
for barium. Well, what's the group 8 element that comes before barium in the periodic table? The group 8 element that comes before barium.
The noble gas before it?
Yeah,
Kr. It's krypton.
krypton.
Krypton, yeah.
So in this case here, the abbreviated version would be Kr.
Oh, I just meant for zirconium. What's its atomic abbreviation?
Oh, you mean the symbol?
Yeah.
Oh, I'm sorry. I think it's ZR if I'm not mistaken. Yeah. Okay. I thought you were asking for the abbreviated version of that. Anyway,
Sorry.
all right, no problem. Okay, so for zirconium 40, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, so that's 30. And then no, that's not 20, that's 20. Then 3d10, that's 30. Then 4p6, so that's 36. 5s2, so that's 38. And therefore 4d2, that would be 40. Let me check and make sure. So that's 10, so that's 20, 36, 38, and 240. So that would be the electronic configuration of zirconium. All right? Okay, any questions about this? Any questions? Any questions? All right, so let me go back to the PowerPoint because we need to cover something before we can proceed to the questions below the ones that we have just looked at. So let me clear this first. And let me go to the PowerPoint. Okay, so make this full screen. Okay, here's we might as well work this example. Write the electronic configuration for sulfur using both SPDF and orbital diagram. So first thing we would look for is the atomic number of sulfur, which is what? Okay, what's going on with this? This thing is, okay. Okay, the atomic number of sulfur is what? 16, right? So therefore, 1s2, 2s2, 2p6, and then 3s2, and then 3p3, right? Because that is 10. No, what am I? 3p4. My bad. All right. So that would be, this is the SPDF notation. Now, to do the same thing for orbital diagrams, that's the 1s situation. This would be the 2s situation. And then as far as the 2p is concerned, there are 3 of them. And the way we put the electrons in is that we put them in singly first within each orbital. And then we pair them up with electrons of opposite spins. And then that takes care of the 3s. So this is 2s, this is 3s. And then when it gets to the, no, this is 2p, I'm sorry. And then when it gets to the 3s, 2 electrons in the 3s sublevel. And then when you get to the 3p, there are 3 of them. So we do it like this. 1, 2, 3, and then we pair up, and that would be the 3p sublevel. All right, and that's it. That's how that is done. All right, any questions about this? Any questions? Any questions out there in Zoom? Okay. Let's see. Oh, okay. So as a result of what we were describing, how you write down electron configurations, what you'll find is that there are certain patterns that emerge with respect to the elements and their positions in the periodic table as it relates to their respective electron configurations. All right. What you'll find, for example, is that there are certain elements that belong to what is called the main group part of the periodic table, which is represented by the blue colored boxes here, right? So groups 1, 2, and then you have 3, 4, 5, 6, all the way to 8 on the other side there. Those are called main group elements. And what they have in common is that as you go from left to right of the period within those groups, you're adding an electron to either an s orbital or a p orbital, right? So that's basically what they have in common as far as the main group elements are concerned. Now, as far as the elements within this region, which is called the transition elements, what you'll find is that what they have in common, again, going from left to right of any period within that group, is that you're adding an electron to an inner principal shell. So not an outer shell or a valence shell, but you're adding an electron to an inner principal shell. And then finally, for the elements that are in the transition region, well, it's actually the same thing that we just said in the transition part here. So let me show you a more explicit picture or diagram of the periodic table, which shows you how the sublevels are adjusting in terms of the number of electrons being added to them as you go from left to right of any period. So I mentioned the main group elements, which would be groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. That group can be further subdivided into what is called the S block and the P block elements, right? The S block elements are basically elements in groups 1A and 2A. And what they have in common is that as you go from one element to the next, you're adding an electron to an s orbital, right? So that's the reason why they're called s block, all right? And then over here for the p block elements, they're so-called p block because, again, you're adding an electron as you go from one element to the next across a period. You're adding an electron to a p sublevel, all right? And then down here in the valley here, where we have the transition elements, they're called the d block elements because, again, going from left to right of the period or any period within that group, you're adding an electron to the D sublevel. And then finally, for the inner transition elements, they're also called the F block, again, because as you go from left to right of any period within that group, you're adding an electron to an F sublevel, right? So that's basically how these elements end up in their relative positions, primarily because of their electron configurations, all right? And what sublevel is being filled as you go from left to right of those different respective regions, all right? Okay, another thing I want to point out is that, and this is true more so for the main group elements than the others. If you look at any one of these periods within that region, what you'll find is that in the outermost shell, which is called the valence shell, we're going to talk about that later on. In the outermost shell, they will have the same number of electrons, right? So if you take, for example, group 4A, right? And you look at the elements starting from carbon to silicon to germanium and then some others, what you'll find is that each of them will have 4 electrons in their outermost shell. So for example, in the case of silicon, the third shell, which is the outermost shell, will have 2 electrons in the S sublevel and 2 electrons in the 3p sublevel, all right? And if you were to continue down to the element below silicon, which is germanium, then the numbers here would be 4s2, 4p2, right? Say a different shell, but the number of electrons in that valence shell will be the same, all right? Okay, so those are just some patterns that emerges as a result of the electron configurations for the different elements. Okay, so this question is asking for you to determine the ground state configuration of strontium, the formula of which is SR, in both the SPDF notation and the noble gas abbreviated notation, right? So again, I'm going to need your help. What's the atomic number of strontium?
What's the
SR.
SR?
30,
Mhm.
38.
38. Okay. So let's do the SPDF notation first. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right. So that's 20. And then 3d10. So that's 30. What's the next sublevel after 3d?
4P.
4p. 6. And then what's the next sublevel?
After 4P.
Mhm. I'm sorry?
5S.
5s. And that would be 2. All right. So that would be the SPDF notation, the complete ground state configuration, right? Now, for the abbreviated version, what we have to do, as I said before, is look at the periodic table and look for the group 8 element that comes before, immediately before strontium. So can somebody tell me what that element is? What group 8 element comes before strontium in the periodic table?
Before strontium.
Mm-hmm.
Krypton.
Krypton. And the atomic number of krypton is what?
36.
36. All right. So basically, that part that I'm showing you now, that's basically the electronic configuration of krypton. So therefore, the abbreviated version would be Kr5s2. And that's it. All right. That's how you get the abbreviated version. Okay. Any questions about this? Any questions? Atomic number? Because you said it's 36, right? 36 basically takes care of what I just showed you.
Can't you just go to the last P subshell since all noble gases
Oh.
are number P?
As you're going to see, no, you can't do that because you're going to see in at least one of the questions that we're going to do here. You can't just do it like that. You have to look at the group 8 element that comes before it and identify that part within the configuration and put that in square parentheses and write down the rest. You're going to see. Okay. Any questions about this one? Any questions? Any questions? All right, let me see what next comes. Okay, so this is where we're going to get to some exceptions to what we were discussing, right? So basically, just to recap a bit, in order to distribute the electrons among the sublevels, you start from the lowest, right? When one sublevel is full, then you go to the next one, and so on and so forth. Of course, if you have a degenerate set of orbitals, you put the electrons singly, and then you pair them up until that sublevel is full, and then you move on to the next sublevel and so on. That's what we have been doing all along. What you're going to find is that there are a couple of exceptions to what we just did. So what I'm going to do is we're going to look at the electronic configurations in certain elements in period 3 or 4. I don't remember. I don't have the periodic table in front of me. But starting, I think it's 4. Which starts with potassium, then calcium, and then the next element is scandium. We're going to start with scandium. Now, before we look at the trends, I want to point out one error here in this diagram here. I wish I could change it. But anyway, the error that you should make note of, because that's important too when it comes to the electronic configuration, is that the 4s sublevel is always of a lower energy compared to the 3d sublevel. So in actual fact, this should be here, and this should be here, right? Because the 4s sublevel is filled up first before the 3d sublevel, right? And that also means that this is incorrect here. 4s should go here, and 3d should go there, right? And that is true for all the others below, right? So I want you to keep that in mind when we're going through the changes, right? As you go from one element to the next across that period. So we're going to start with scandium. Scandium has an electronic configuration which is represented here, right? So this represents the part of it which is equivalent to argon. Then you have one electron here in the 3d sublevel, and for the 4s sublevel, there are 2 electrons. Remember now, the 4s sublevel is before the 3d, so it should be 4s, then 3d, all right? So this is basically the situation for scandium. To get from scandium to titanium, we have to add one electron to what we have here. And that one electron can go into any one of these vacant orbitals, right? So that electron will be added here. And you'll notice that this electron has the same spin as this electron, right? The next element is vanadium. To get from titanium to vanadium, we add one electron to any one of these three structures, right? Or these three orbitals. So that gives you this right here, all right? Now, here's where the exception will occur. Now, you would think, based on the trend that we have established so far, that to get from vanadium to chromium, you simply add one electron here, right? It turns out, and there's a long story behind that in terms of experimental data and so on, it turns out that that is not the ground state configuration. Not only do you add one electron here, right? But also you take this electron and transfer it here, and that will give you now the configuration which is the most stable, all right? So basically, the result is that you have a half-filled D sublevel along with a half-filled S sublevel, and that is more stable than what you'd expect, which would be this right here, all right? So that's one notable exception that you need to be aware of when it comes to chromium, all right? Okay, so once we establish that, then the question is, how do we get from chromium to manganese? And the answer is you add one electron, and that one electron will be added to the 4s sublevel, because that 4s sublevel is of a lower energy compared to the 3d sublevel, all right? And then to get from manganese to iron, you add one electron to any one of these d orbitals. So we add it here, and of course, when you're pairing, the electron must be spinning in opposite direction, right? To the first one. And then to get from iron to cobalt, you add one electron here, that gives you this. And then to get from cobalt to nickel, you add one electron here, and that gives you this configuration. And then we get to another exception. And the other exception is, you would think, again, following the trends, you'd think that to get from nickel to copper, you just add one electron here, and that's it. But no, you have to not only do that, but you have to take one electron from here and put it and pair it up with this electron right here, and you end up with this configuration, all right? So in this particular case, as stated in this green box right here, a half-filled 4s level and a completely full D level, 3D level, is more stable than what you'd expect otherwise, all right? So that's another exception when it comes to using the Aufbau principle to adding electrons or to determine how electrons are distributed among the different orbitals, all right? So please make a note of those two exceptions. And let me just say also that these exceptions apply also to elements below chromium and copper in that group in the periodic table, right? So someone with a periodic table, what's the element immediately before, not before, below chromium, Cr? What element is below chromium?
MO.
Hmm?
Below chromium is CR, it's MO, it's, I don't know. what
Oh,
the-
MO,
the-
molybdenum, right? So in the case of molybdenum, for example, right, its electronic configuration, if I'm not mistaken, is, what's the element below argon in the periodic table?
Krypton.
Krypton, okay. So in the case of molybdenum, the electronic configuration will be krypton in square parentheses, and then you're going to have 4d5, 5s1, right? That would be the configuration in the case of molybdenum, and not 4d
44, 5.
44, 5s2, right? This would not be the electronic configuration for molybdenum, right? For the same reason as I mentioned before, all right? Okay, so those are the exceptions to the Aufbau principle. So going back to, hold on, let me just check something here. Okay, going back to,
There's the only three?
no, the one below copper will do the same thing or do something similar.
Silver?
Yeah. Okay, somebody said, oh, somebody was answering the question I asked earlier. Okay, thank you, Miss Anwar. I didn't see your message, your text. in time. Okay, so let's go to the assignment. So in the case of the second part of part A, you're asked to write the abbreviated, not the full, but the abbreviated electron configuration for the different elements. Okay, so in the case of cobalt, turn on my pen. What's your atomic number of cobalt? Can somebody tell me?
Cobalt,
Hmm.
27.
27. So what I would do if I were you, since you're learning this for the first time, I would write down the full configuration first. So in the case of cobalt, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d7. All right? So this would be the full electron configuration. Now, to get the abbreviated version, what we do, we go to the periodic table and we look up the group 8 element that comes before cobalt, and that would be what?
Argon.
Argon. So put argon in square parentheses, which should be representing this power right here. And then we write down 4s2, 3d7. And that's it. All right? Any questions about this one? Okay, next one is silver. Again, what's the atomic number of silver? I'm sorry?
47.
47. Okay. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So that's 30. And then what comes after 3d? Is it 4p?
After 3D,
4P.
4p, that would be 6. So that's 36. And then what's after 4p? 5s. So that's 36 plus 2, that's 38. And then what's after 5s? 4d. So that's 4d. Okay, so this is where one of those exceptions occur, because I was just following the trend and I end up with 4d9. However, what will happen is that one electron will go from here to here. So you're going to end up with 5s1 and 4d10, right? So again, we have a situation where we have a half-filled 5s sublevel and a 4d completely filled sublevel, all right? So that is more stable than what I had before. So that would be the full configuration, but we're asked for the abbreviated configuration. So again, we have to consult the periodic table and see what's the group 8 element that comes before silver. Krypton, all right? So krypton, if I'm not mistaken, will take care of all, hold on, what's the atomic number of krypton? I'm sorry? 36. So, okay. So this here is basically the electron configuration of krypton. All right? So basically, all we have to do after doing this is 5s1, 4d10, and that's it. All right? Okay, any question? Oh, I'm sorry. Yes, sir.
those 4 elements, chromium, copper, silver, and the other
Those are the ones, right? Those are the ones that you should note as the exceptions in terms of applying the off-ball principle.
and those are the only 4.
Well, yeah, at this level anyway, yeah. And let me just say this, things get real confusing when you get to the lower, heavier elements. So I'm not even going to delve into that at this level, all right? Okay, tellurium. What's your atomic number of tellurium? 52. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. So that's how much so far? That's 10 plus 10 plus 10, 36, 38, 48. So what comes out to 4D? 5p. So 48. So we're going to need 4 here. So that would be the full electron configuration. All right. So what's a group 8 element that comes with 4? Tellurium, krypton. So again, krypton takes care of all this right here. So therefore, krypton in square parentheses, followed by 5s2, 4d10, 5p4. And that would be it for tellurium. All right. Okay, any questions about that one? Any questions? Okay, the next one is radium. What's the atomic number of radium?
88.
88. Oh, this would be a very long one. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 5p6, I'm sorry, 4p6, 5s2, 4d10, 5p6. Okay, so that takes care of, that's 54 so far. So what's the next sublevel after 5p?
6s.
6s2, and what comes after that?
5d.
5d?
Yes, sir. It's
Oh.
gonna go all the way to 10.
5d is 10. So let's do a quick check here. So 54 plus 2, 56. 56 plus 10 gives you 66. Okay, so what comes after 5d?
6p.
6 what?
6p.
6p6.
Yes, sir. 7s2.
7s2.
That's it. 4f, yeah.
Oh,
I missed that.
I'm just following what he says because I don't have.
I didn't see the line. I skipped that.
Okay, so after 6p, yeah, there's 4f.
Yes.
Oh, before 5d, my bad, hold on. So let me erase that here. So after 6s2 is 4f, and that is 14, right? So let's do a quick check here. So up to here, it's 54. 54 plus 2, that's 56. 56 plus 16 gives you what? 70, right? So what comes after 4f?
Then it's 5d.
5d, which would be 10. And then so that's 54, 58. No, what am I saying? Okay, I'm confusing myself. Up to here would be 54, 56, 70, and 10, 80. And then what comes after 5D?
6p.
6 what?
6p.
6p6. And then what comes after that?
7s2.
7s2. Wow, okay. So the group 8 element that comes before this is what?
I don't know the name of it. The symbol is Rn.
Radon. Okay, so Rn, which would take care of, and Rn has an atomic number of, let me guess, 86?
Yes, sir.
Okay, so that takes care of everything here
To 6p.
up to 6p6, right? So therefore it's Rn in square parentheses followed by 7s2. And that's how you do that. All right? Any questions about this one? Any questions? Okay, rhodium. What's the atomic number?
Rh.
Yeah,
Symbol 45.
45. All right. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, so that's 30. Then 4p6, so that's 36. And then after that is 5s2, so that's 38. And then we have 4d. So 38 from 45 gives you what? 7. So that should be it. All right? 10, 10, 10, that's 36, 38, and 7, 45. So that's the full. So what's the abbreviated? What group 8 element comes before rhodium? Krypton, which is
All the way up to 4p6.
all the way up to 4p6. So therefore, it's krypton, Kr, in square parentheses, followed by 5s2, 4d7, and that's it. Okay, so that's basically how you determine the electron configurations, both the expanded or full configuration and the abbreviated version. All right? Okay. Is it okay for me to clear this? All right, so let me clear this and let me scroll down. Now, the latter part of the A part is actually easier than what we have been doing, because basically what they're asking for you to do is to determine the elements. And all you have to do in order to do that is to count up the number of electrons. And that's it, right? And then you look at the atomic number that matches up with it in the periodic table, and that's how you determine the element. So in the case of the first one, all we have to do is add the number of electrons shown. So that's 2 plus 2, 4, 10, 12, 16. So therefore, the atomic number is 16. So that matches up with what? No. Sulfur. Oxygen is 8. Okay. Then in the case of the next one, it's 2 plus 2, 4, 10, 12, 18, 20, 30, 36, 37. Which element matches up with 37? Atomic number.
Rubidium?
I think that's right.
Yeah.
I mean, I don't have the periodic table in front of me, so, but I think you're right, okay?
It's Rb.
Right, Rb, yeah. Then, in this case, they have krypton in square parentheses, right? So what's the atomic number of krypton? 30 what? 36. So we add 36 to 2, that's 38 plus 10, 48, 48 plus 3, 51. So which element matches up with an atomic number of 51? Antimony. I think that's right too. SB, yeah. Okay, next one, xenon. What's the atomic number of xenon? 54. So we add 54 to 2, that's 56. 56 plus 14 gives you, what, 70? And then 70 plus 6 gives you 76. So what element matches up with that? I'm sorry?
Osmium.
Osmium, okay. And then finally, radon. What's the atomic number of radon? I'm sorry? 86. So we add 86 to 2, so 88. 88 plus 11, that's 99. That corresponds to what element?
It's got the symbol FM. It's right after Einsteinium.
Einsteinium? Is it Einsteinium?
No, it's the one right after.
Or the one right after? Okay, I'll be honest with you. I don't know what the name. It's FM?
Yes, sir.
Okay, I don't know what's the name of that. Yeah, 99?
F11 isn't F11 100? Or am I wrong?
86 plus 2, 88 plus 11.
Okay, yeah, 99. So it'd be Einsteinium.
Einsteinium, okay, my bad. Okay. So Einsteinium, or how do you spell it? I think that's how you spell it. Okay. So that's it as far as that is concerned. All right. So that's relatively simple compared to the previous ones that we have looked at. Okay, let me scroll down to see what's next. Okay, we can't do that yet. So let's go back to the PowerPoint. Okay, somebody, oh, I'm sorry, Mr. Anwar, I keep missing your messages because I'm so focused on doing these problems. But yeah, that's sulfur to answer your question. All right, so let me clear this. And let me go back to the PowerPoint. All right, so now we're going to talk about the difference between what is known as the valence electrons. I kind of briefly alluded to that term earlier. So we're going to talk about the difference between the valence electrons and what we call the core electrons, right? Now, the first thing we're going to define is the valence shell, right? Which is the outermost occupied shell of the atom, all right? And the electrons that are located within the valence shell, we call them valence electrons, all right? So what you'll find, again, based on the patterns that emerge in the periodic table, is that when it comes to the main group elements, the number of electrons that would be occupying the valence shell is equal to the group number, right? So for elements in group 1A, the number of valence electrons present in those atoms would be 1. In the case of elements in group 2A, it would be 2, and so on, right? And that is true for the main group elements, right? Now, when it comes to the transition elements, you cannot make such a correlation. It's messy and all that. So we cannot make a correlation between the number of valence electrons and the group number for the transition elements, right? Another thing that we need to understand is that when it comes to the period number, now the period number are basically the numbers for the rows, right? Very simple system, 1, 2, 3, 4 as you go down, right? What you'll find is that the period number correspond to the shell number that is occupied by valence electrons, right? So for example, I think oxygen is in period 2, right? And basically the valence shell would be the second shell, all right? Or in the case of something like like phosphorus. Phosphorus is in what period? 3? Can somebody check and make sure? Or what row? Is it the third row?
Phosphorus?
Phosphorus, P.
Yeah, third.
Okay, good, right. So basically, by virtue of the fact that phosphorus is in the third row, you can tell that the valence shell in the case of phosphorus is the third shell, all right? Okay, now those are the valence electrons, the electrons that occupy the outermost shell. All the other electrons within the structure are called the core electrons, right? So we have an example here. In the case of arsenic, this would be the full electron configuration. Well, actually, the abbreviated electron configuration of arsenic, right? So in terms of the valence electrons, those are the electrons occupying the outermost shell, or the shell with the highest n value, quantum number, right? So basically, the orbitals or the subshells in the valence shell would be the 4s and the 4p subshells. And therefore, the total number of valence electrons that would be in the arsenic atom would be 2 plus 3, 5 electrons, right? Now, in terms of the other electrons, the core electrons would be the rest, right? Including the 3d sublevel here, that has 10 electrons, and then you have 18 electrons from the argon. So the total number of core electrons in the case of arsenic would be 18. So you have 18 core electrons, you have 5 valence electrons, all right? Okay, so that's as far as the difference between valence electrons and core electrons are concerned, right? Now, it's very important that you understand that distinction. What time is it? Okay, let me mention this quickly and then we call it a day, right? It's very important that you understand the distinction between the core electrons and the valence electrons when it comes to determining the configurations of ions. So before we were talking about the electron configurations of atoms, now we're going to talk about the electron configuration of ions, right? And we know that there are 2 types of ions. You have positive ions, which are the cations, and you have the negative ions, which are the anions, right? And we all know when it comes to monatomic ions, if you want to get from the atom to the anion, you add an electron or 2 or 3, depending, right? If you want to get from an atom to a cation, then you subtract electrons, right? So that's what you have to take. You have to keep in mind when you're determining the electronic configuration of monatomic ions, right? Now, let's deal with anions firstly. To obtain the electron configuration of an anion, all you have to do is simply add electrons according to the Aufbau principle. And basically, what you'll find, especially when it comes to the group 8 elements, that adding electrons usually completes the shell. In other words, the shell would be full as a result, right? And as a result, as well, the monatomic ion, if it's non-metal, will obtain the same electronic configuration as the nearest group 8 element, all right? So I have an example here. So the oxide ion, for example, will have the same electronic configuration as neon. The bromide ion will have the same electronic configuration of krypton, right? Because neon is the nearest group 8 element to oxygen. Krypton is the nearest group 8 element to bromine. So basically what will happen is that in order for these elements to form their monatomic ions, they will gain the same number of, well, they gain enough electrons so that they end up with the same number of electrons as their nearest group 8 element, all right? So that's what happens when you have the formation of an anion from an atom, all right? Now, the opposite is true when it comes to metals and their atoms forming cations. What they do is that they lose electrons, right? So basically, electrons will be removed from the electronic configuration of the metal atom. And the question now becomes which electron is removed? And the answer is that the electron that occupies the highest n value shell is the one that will be lost first, all right? Now, if there are two subshells within the same valence shell, then the electrons are lost from the subshell with the higher L value, or the one that has a higher energy, all right, within the shell, all right? So let's look at some examples right here. So, okay, so the first two is dealing with the formation of anions. Again, the atom will gain electrons to form the anion. In the case of fluorine, it's going to gain one electron. That electron will add to the 2p sublevel. So you're going to end up with this electronic configuration, which is the same as that of neon. In the case of sulfur, this is the electronic configuration of sulfur. It will gain two electrons to completely fill this 3p sublevel. And you're going to end up with this right here, which would be the electronic configuration of the sulfide ion, which is the same as that of argon. Now, let's look at what happens when you start losing electrons to form the cations. Again, this is typically what metals will do. In the case of strontium, right, it will lose these two electrons here to form the strontium 2 plus ion. So when it loses those two electrons, it ends up with just the electronic configuration of krypton. In the case of titanium, it can lose these 4 electrons, these two here, and these two here, and you end up with the titanium 4 plus ion, which has the same electronic configuration as argon. Now, in the case of iron, and this is where you have to pay attention closely to how you get the ions, right? If you want to go from iron atom to iron 2 plus ion, you have to lose 2 electrons, right? The first electron will be lost from the 4s sublevel because that's the higher energy shell, right? So the first electron will be lost here, right? The next electron will be lost from here as well, right? So that 4s sublevel will disappear, and therefore, as a result, the remaining electron configuration would be this right here, right? Ar3d6, right? And just to follow up, let's say you want to find out what the electronic configuration of Fe3 plus is, right? Then basically you're going to remove this one electron here, and therefore the resulting structure would be Ar3d5. And that's basically how that works, right? So in the case of the formation of cations, you start losing electrons first from the orbital or the sublevel that is belonging to the highest energy shell, all right? And that's basically what that comes down to, all right? So I just answered the question for this here. Let's see if we can quickly answer the question in relation to tin 2 plus. Now, the electronic configuration of tin is, oh gosh, what's the group 8 element that comes before tin? Can somebody tell me? Krypton. And if I remember correctly, krypton is in the 1, 2, 3. Is it in the 4th row, krypton? Okay. So if I'm not mistaken, the electronic configuration of krypton would be, I'm sorry, of tin would be 5s2 4d2, right? So if you want to find out what the electronic configuration of Sn2 plus is, you're going to lose the electrons from here, right? Because this is of a higher shell. So therefore, the electronic configuration of krypton will simply be this. And that's it. All right. I'm going to stop here for today, and we're going to continue our discussion of this chapter on Friday. All right? All right, so I'll see you then.
Will we be able to get to chapter 10 semester or
Yeah, we should.
then the test 3 would be like between chapters, what, 6 to 10?
No, in fact, I don't think so because the last test was based on chapters.
So yeah, I can use it.
Hold on 1 minute. The last test was based on chapters.
Yeah, that's
3, 4, 5, right. So yeah, I would say at least 6, 7, 8, maybe 9. I'm not sure, but 6, 7, 8 definitely.
So the 9 and 10, like depending on like how it ends up being towards the end of the semester, like that won't be on the test 3.
No,
So will that be on the final?
final. It will be on the
Okay,
final.
okay.
Exactly.
So all right, that makes sense.
Mhm.
All right, thank you.
But definitely for the next test, definitely chapters 6, 7, and 8.
Okay.
Yeah. Yes, sir.
just about my test 1, it's still in the grade book is a 69.
Oh, I'll get to it later on today. I keep overlooking some minor stuff.
Yeah, it's fine.
But yeah, I'll get to it.
Thank you.
Mhm. Okay, let's see here. Yeah, there's Miss Anwar, I'm going to switch over to that link right now as soon as I sign out from here. So all right, so I'm closing this out. I've been going over to the STEM